So phase one, we isolate the exponential expression, we subtract the 15. So negative 40 e to the x plus 4 equals negative 1020. And then divide off the negative 40. And then e to the x plus 4 equals a positive 26.
25.5.
Oh, 25.5. My goodness. Okay, great. All right, well, this looks a lot like the last problem. We've isolated the exponential. Again, thinking about our methods, we could either equate the bases, but no, 25.5 is not the power of anything. Easy. So then we can just convert it into log form. So we would say log base e of 25.5 is equal to x plus 4. And now again, log base e, I just write it that way at first so that I just see the quick process of how to do, log base e of 25.5 equals the exponent. Or if you just feel comfortable immediately writing down log ln, you can do that. So now we have ln 25.5. That's just something you can type in your calculator. X is being added by 4, so you subtract. And we end up with x equals natural log 25.5 minus 4. What's ambiguous about the way I wrote this? It is ambiguous. If somebody was just looking at this work, like if I fell asleep or I was just gone, and someone came over and said, ln 25.5 minus 4, does JW mean ln 25.5 and then minus 4? Or does he mean ln 25.5 minus 4, which, hey, why didn't he simplify that? That's just ln 21.5. So it's a little ambiguous. And depending on how you type that into your calculator, that could be ambiguous too. So perhaps even better would be to wrap that in parentheses so that everybody knew that that's one thing, and then you subtract 4. Again, I think parentheses are so important. It's so important that we continue to talk about parentheses and the proper way to use parentheses. The whole point of parentheses is to avoid ambiguity. You know, to avoid ambiguity when you tell people things. Parentheses, perhaps you've seen this joke. I hope this is a good joke. I think it's very funny. It's a joke where it says commas save lives. Maybe you've already seen this meme online. Commas save lives. So there's two different statements. One of them is, let's eat, Grandma. Like you're calling to Grandma in the other room of the house, and like you finished cooking food, and you're like, let's eat, Grandma, and you're calling her in. Or versus the other phrase, let's eat, Grandma. Right? So commas and parentheses serve a very similar purpose. Commas avoid ambiguity in English. Parentheses avoid ambiguity in math. So that's a joke. Okay, we're not going to do 13 or 14, so let's move along. And we're moving into section 6.4. So now we're doing something completely different now. What do you notice that's different about all of these equations on the next page? Yeah, now these are all log equations. These are all log equations. So our approach is going to be a little different. Right? We just finished talking about how to solve exponential equations. Now we want to solve logarithmic equations. Yeah. The ln. Well, you type that into your calculator now. I didn't even type that into my calculator, folks. What was the final answer? ln 25.5 minus 4. Did everyone get negative 0.76?
Yes.
Yes, a negative 0.76. All right. So in this case, we're now solving for, we're solving logarithm equations. Now, there's a variety of ways to do this. Just like we had a list of 3 different ways to solve an exponential equation, now we're going to have a list of multiple different ways to solve a logarithmic equation. So that was solving exponentials. Now let's talk about solve log equations. And we'll make our list of methods as we go. So we'll just look at each example and see what it tells us. So first take a look at number 1. And yeah, I don't want to read that yet. Let's wait and do some examples, and then we can go back and read it. So we've got log base 5 of 18 minus x squared equals log base 5 of 6 minus x. What can we say about this statement? Here we have a common log 5 on both sides. I'm saying log of something equals that same log of something. So what do you know for sure must be true about the objects under my hands?
Equal.
Yeah, they have to be equal to each other. Everybody really look at that and make sure that that's really, really crystal clear logically to you. That if I want these two sides to be equal to each other, log base 5 of something equals log base 5 of something, whatever's underneath my hand had better be the same. Because, for instance, would you all agree that log base 5 of 7 is equal to log base 5 of 7? Is that immediately and obviously true? And you don't even have to think anything about logs. You don't have to know even what a log is. I should be able to show that to a child who at least knows what equals means. And the child would be able to say, well, sure, that's true. I don't know what it means, but it's true. So, and likewise, would log base 5 of 7 be equal to log base 5 of 3? Can you even imagine a universe in which that's true? And that'd be pretty tough to sell to anybody. Again, even a child would be able to say, well, that I don't know what a logarithm is, but the left-hand side is not the same as the right-hand side. So those can't be equal. So what we're saying here is that so long as you have the same log of both sides, these two things must be the same. So this must be equal to this, and you just write down a new equation. 18 minus x squared is equal to 6 minus x. It must be true. And at this point, you just have a normal equation that you just solve. Now notice, this is the exact same technique as equating the bases. Like 2 to the x equals 2 to the 3. If the bases are the same, the exponents must be the same. Here, if the logarithms are the same, the arguments must be the same. And that's what we're saying. Equate the logs. If you equate the log, then you can equate the argument or the input. All right, well, we can go ahead and solve the quadratic real quick. Let's move the x squared over to the right. That's what I'm going to do. I'll move the 18 over to the right. That's what I'm going to do. So now I have 0 equals x squared minus x minus 12. Anyone else get that? Yeah. So then can we factor that? What multiplies to make 12 that adds to make 1? Yeah, 3 and 4. So now x minus 4, x plus 3. And now I can use the zero product rule and say either x equals 4 or x equals negative 3. Now, if this was a quadratic, if this was a parabola, there would be two solutions. Because that parabola, x squared minus x minus 12, would look like this. And therefore, there would genuinely be two solutions because there are two x-intercepts. Right? So at least as far as this equation goes, there are two solutions to that equation. But that equation is not the original equation. This is the original equation. And we need to know, do both of those solutions work in the original equation? That's what solving for x means. Solving for x means find a number that you can plug into the original equation to make it true. That's what you always have to remind yourself. Don't just, if you just do a bunch of algebra, algebra might lead you somewhere. But that doesn't mean both of those are correct. Maybe only one of them is correct. Maybe neither of them are correct. So now let's plug it in. Can I plug 4 in? That would be log of 18 minus 4 squared is 2 equals log of 6 minus 4 is 2. So yes, x equals 4 definitely works because it leads to the true statement log 2 equals log 2. Notice I don't need to know what log 2 is. It's like 0.38. But the point is it's a true statement. Now, can I plug in negative 3? If I plug in negative 3 over here, that would be log of negative 3 squared is 9, 18 minus 9 is 9, equals 6 minus negative 3. 6 minus negative 3. Ooh, that's also 9. Okay, gumdrops. Both solutions work. You were all expecting that second one not to work, right? I mean, I was expecting that second one not to work, but no, it worked. So now both solutions are true. It all worked out. So that problem really did have two solutions. All right, so that was one potential method. Solving a logarithm equation. One method is to equate the logs so that you can equate the arguments. All right, number 2. I bet you can all go ahead and figure out how to solve this one. What could we potentially do here? It is actually one of our methods from previous. We want log base 3, 7 minus 2x equals 2, and we want to get x by itself. What could we do? What do you want to suggest? You could good point. You could somehow rewrite 2 as the log base 3, right? I mean, wouldn't that be nice if on this side we had log base 3? And so wouldn't it be nice if on this side we also had log base 3? Wouldn't that be nice? Sometimes this is called making it so. Like, I wish both sides were log base 3, so I'm just going to force the issue and make the right-hand side log base 3. Log base 3 of what would equal 2? What number would I have to put here? Such that 3 to the what equals a number would be the answer 2. What number would I have to put there? It's confusing to think about. I want to put a number there. Well, let's just say I start by putting the number 3. 3 to the what is 3? 1. That's not what I want. So what number would I have to put there? You can always just start thinking powers of 3, because those would be convenient numbers to put here. What about 9? 3 squared is 9. 3 to the what is 9?
2.
3 to the power of 2 is 9, and that is exactly what I want right there. So yes, in fact, this would work. You could always rewrite the 2 as a log expression. So does everyone agree that log base 3 of 9 is equal to 2? Because all we did right there is we just very cleverly rewrote 2 as a log. And why? Now what can we do? We have the same log on both sides, therefore 7 minus 2x must be equal to 9. And the logarithm parts just fall away, and you're just solving that simple equation. Now, who suggested that we rewrite 2 as a log? Actually, that's perfectly fine. It was one of the 2 solutions I wanted to show you. It's potentially the harder solution because you have to sit there and think, how can I rewrite the number 2 as a log base 3? It hurts the brain a little bit until you're used to it. So let me see. Let's go ahead and finish solving this. I'm going to add the 2x over to here. And so now I have 7 equals 2x plus 9. Then I'll subtract my 9. And now I have 2x equals negative 2. And therefore, x equals negative 1. Now, surely no one in the room wrote down x equals negative 1 and said, OK, great, next problem. Right? Because we all now know that writing down x equals is not the end of the problem. We didn't finish the problem yet. Is x equals negative 1 really a solution? We don't know yet. We have to plug it back in. So let's plug in negative 1. So that gives us check. That's my check part. So log base 3 of 7 minus 2 times negative 1. Well, that's really log base 3 of 7 plus 2, which is 9. And what's log base 3 of 9? 2. So yes, the answer works. X equals negative 1 is the solution. All right, now I'm going to show you there's an easier way to do this problem. What's another method that we can use that's written down over here? Anytime you're given any expression, exponential or logarithmic, what could you do? You could switch it to the other expression. So take a look at number 2 here. If they give you a logarithm expression, switch it to an exponential expression. If they give you an exponential expression, switch it to a log expression. So method number 2 is convert from log to exponential. Just like before, we were converting from exponential to log, now convert from log to exponential. So if I have log base 3 of 7 minus 2x equals 2, how do I convert that into an exponential expression? Left to the right equals middle. Left to the right equals middle. 3 squared equals 7 minus 2x. 3 squared is really 9 equals 7 minus 2x. How nice is that? I think that solution is much faster, much easier. Plus, it's one of the fundamental things I want you to internalize. Convert from exponential to log, convert from log to exponential. That's almost always the way to solve an exponential or logarithmic equation, is to simply convert it to the other form. This obviously has the same solution. X equals negative 1. All right, so this method that we just said is what we're going to be using over and over and over again. Is just convert from log to exponential. So for instance, take a look at number 3. What would we do here? This is the log form, so we should convert it to exponential form. So instead of log base of half of 2x minus 1 equals negative 3, we'll go left to the right equals middle. Worth writing down if you don't already have it memorized. Left to the right equals middle. So 1/2 to the power of negative 3 equals 2x minus 1. Now just temporarily might 1/2 to the negative 3 look bad. Like, oh no, it's a fraction raised to a negative exponent. But ironically, the fraction and the negative exponent cancel each other out. What does a negative exponent mean? To do the reciprocal. So this is actually very convenient. 1/2 to the negative 3, that's really 2/1 to the power of positive 3. And I just wrote 2 instead of 2/1. 2/1 is just 2. So now 2 cubed, 2, 4, 8. You've all been practicing your powers of 2 as you walk around. 2, 4, 8, 16, 32, 64, 128, 256, 5, 12,024. You've all been practicing that as you walk around campus and eat lunch and all that. So 8 equals 2x minus 1. So 2x equals 9. And so x equals 9/2, which is 4.5. So we just wrote down x equals 4.5. We all know that's not the end of the problem. We still have to now plug 4.5 back in and see if it works. So let's plug 4.5 back in. 2 times 4.5 is 9. 9 minus 1 is 8. So that gives us log base 1/2 of 8 equals negative 3. And we ask ourselves, is that a true statement? Is it true that log base 1/2 of 8 equals negative 3? What's one thing you could do to check that it's true? Yeah, you can just plug that into your calculator, right? Using the change of base rule, you can do log 8 divided by log 0.5. And if you all type in right now log 8 divided by log 0.5, your calculator will tell you negative 3. Everybody try it. It's worth trying. So if I type in log 8 divided by log 0.5 with parentheses, log 8 divided by log 0.5, it equals negative 3. So one way to check that it's a true statement is typing it in your calculator. The other way is to convert. See, this is a statement. I can now convert this to exponential. So now this is 1/2 to the negative 3 equals 8, which, again, the negative exponent means 2 to the 3 equals 8, and we end up with 8 equals 8. So, folks, I realize sometimes maybe I repeat myself too much. I'm trying to put a lot of emphasis on the truth here. And that is, how did all three of these problems end? This was the end of that problem. This was the end of that problem. This was the end of that problem. What's the end of every algebra problem? Yeah, just a true statement. You know, it almost makes it silly and laughable. The end of this problem was 8 equals 8. Something so laughably, ridiculously simple, 8 equals 8, that any child would understand. The end of this problem was 2 equals 2. I mean, it almost makes algebra sound silly that the end of an algebra problem is just a basic, obvious fact, like 8 equals 8. But that's what algebra is looking for, is truth statements, statements that are true. And so when we say we solved this problem, the solution to this problem is 4.5, because when I plug it in, it gives me a true statement, 8 equals 8. All right, this next problem, number 4, before we do it, maybe you already see how to do the problem. I think it's worthwhile to remind all of you that we can solve all of these by doing what? What's the amazing thing about all equations? How can you solve all equations? You just graph them. Because mathematicians long ago created the system that if you just make a graph, the solution for x is always the what? What point on the graph gives you the solution to an equation? The what? What point on the graph gives you the solution? Like, I'm going to type in this last equation here, natural log of x squared minus 99. What point on this graph is the solution for x? Can you see that? Well, that's the equation. What point is the solution? The x-intercept, right? That's so important, I'm going to write it down as another method. How do you solve a log or exponential equation? Graph it and look at the x-intercept. Graph, find the x-intercept. The x-intercept is always the solution to any equation. Any equation at all that you can think of, if you graph it on Desmos, find the x-intercept, that's the answer. So you can already tell, looking at this problem, that the answer is 10. And in fact, also negative 10. So I already know going into this equation that my answer had better be 10 and negative 10. And perhaps I should zoom out. Are there any more solutions? No, it doesn't look like it. It looks like they move out to the right and left asymptotically. So the only solution I should expect is 10 and negative 10. Again, this is great because anytime you're taking a test, you can cheat, check your answer by just graphing it on your TI calculator and seeing ahead of time what the solution is. And I think that's a good best practice. Like right now, before I even start this problem, I'm going to make a note. X equals 10 and negative 10. I already know. Yeah, that's the answer. So how do we solve this problem? What method are we going to use? What method are we going to use to solve this? Yeah, we're just going to convert. We're going to convert. That's pretty much any given problem you want to convert. So now, ln, in case you want to remind yourself, that's log base e of x squared minus 99. Right? Because ln is just an abbreviation. Probably helpful just to go ahead and rewrite it as log base e so you clearly see what you're looking at. And now, left to the right equals middle. E to the 0 equals x squared minus 99. Well, what's e to the 0? What's anything to the power of 0? 1. So now we have 1 equals x squared minus 99. Move the 99 over. X squared equals 100. And now, very clearly, x equals plus or minus 10, which is the solution that we expected from Desmos. Just to throw out another example, I could also solve this problem by making both sides be ln. How could I rewrite 0 as a natural logarithm problem? If I wanted to rewrite natural log of x squared minus 99 equal to the natural log of something, such that whatever I put there, it's going to give me 0. The natural log of what equals 0? E to the what would the answer be 0? Again, this is tricky to think about. You could just start thinking of powers of e. I could write e right there first. E to the what equals e? 1. And that's not what I want. So instead, what if I put a 1 there? E to the what equals 1? E to the what equals 1? 0. So that is what I want. Now I have a natural log of both sides, and that allows me to say that x squared minus 99 must be equal to 1. I don't know that I've convinced anybody that this is a fun method that you'd want to use, but I just wanted to show again how to take a single number and rewrite it as a log. Okay. Well, what we have going on in front of us here are a few more examples of log problems, and then we have applications, and that's what we'll spend the rest of the day doing. So let's look at a few more ways to solve logarithmic equations. And we'll start right there. Actually, you know what, folks? All of you can go ahead and do number 5 for sure. And I think all of you can go ahead and do number 6. So how about we all spend about 5 minutes working on these 2 problems, and I'll just walk around the room and answer any questions. Feel free to talk to each other, brainstorm with each other. Just converted, and then you move that over. Super. Yeah. No, that will end with 1 base e. Log is 1 base 10. So everyone, just to make sure you're all looking at number 5 in the same way, that log right there is inherently log base 10. There's no number written there, and that means that it must be log base 10. So probably the first thing you want to do is write log base 10 of x squared minus 3x equals 1. It's so important to visually be able to see the base number, because only by seeing the base number will you be able to convert it to an exponential.
Because that is technically one of those things. But so far, you move that over, and that's not helpful to just leave it as. So far, all you did was just write it. So you can see. So that's what you're at so far. Now, how do you convert this to an exponential expression? The left to the right. So now right now, 10 to the 1 equals. And that's how you move that over to the other side. So you're going to write 10 to the 1 equals x squared minus 3x. Yeah. Very nice. So you got your little pen. And now you're not just move that over. I would erase that. What you're saying right now here is that left to the right equals 1. So 10 to the 1 equals actually minus 3. What you're writing on here is just 10 to the 1. There you go. And of course, 10 to the 1 is just 10. So then the next article, we just have 10 equals. Does that make more sense? Work. Nice, nice. That works. Yep. Typically, no matter what, you want to always move all of your terms to one side so that it equals 0. Because then once you move that 10 over, you can factor. So the answer to your question is, you wouldn't factor it like this, and you won't square root it either. You move the 10 over first. Because then you can say what multiplies to make the last number, the adds to the middle number, and do the traditional factor. Yeah. So this is this lowercase 10? Oh, you can word this along with 10 to what equals 10 to what equals, it's not 0. It actually is. Yeah, now look again. 10 to the 1 equals 10. So this 10. Yeah, exactly. That's what we want. Yeah, so I admire that you were trying this technique. You'd rewrite 1 as log this 10 of 10, and that's 1. So now you have log this 10 of that. Just really extra. And you get the same, well, you're going to see much more the same. Now you have this. Oh, and you can get it. Yeah, that's correct. Oh, yeah, so this is, you were doing this method last year. So you did 2 different methods. Perfect, Andrew, that's great. And you'll notice that either way you're going to get the same answer. Good. Yes, sir. You don't divide by 6. 6, you subtract it. 1. Right. Then this one, first of all, is 6 being multiplied by? No. So you couldn't possibly divide. It's not being multiplied. But also, if you want to, you could also rewrite this backwards. You can rewrite this as and now this 3 is the second one. And 6 is the second one. Now it's negative 3 blocks. 6 now it's the very obvious. So that's one thought. Remember what you get whether you're multiplying or writing that. In fact, the numbers is always switch the order and then it's this one last thing. If you get this order x is going to multiply, then multiply by 3. So negative. And then add by 6. And the last thing it says was add by 6. So well, you have this couple hours. You could throw that up there, so it's good. But that's what you see here. I like it. Well, it won't be a 0. That's 6. Oh, so
Very nice. Yeah, I'm glad you graphed it too. Okay, folks, let's check answers for number 5. I've seen everybody's work on number 5, and I didn't quite get to see everybody's work on number 6 yet, but we'll go ahead and review both of these. So in number 5, we are just going to convert from logarithmic to exponential. That's technically log base 10. So left to the right equals middle, 10 to the 1 equals x squared minus 3x. And then we move to 10 over to the other side. We have x squared minus 3x minus 10 equals 0. And so what multiplies to make 10 that adds to make 3? Is it x minus 5x plus 2? And then by the zero product rule, x equals 5 or negative 2. Now remember, that's just where the algebra took us. Algebra and solving for x are not one and the same. Now we have 2 candidates for what the answer would be. So now we plug 5 in. This either gives us log of 5 squared is 25 minus 15. That's log of 10 equals 1. That's true. Log base 10 is equal to 1 by definition. 10 to the 1 equals 10, so that's true. Or I plug in negative 2, so that would give me log of negative 2 squared is 4. Minus 3 times negative 2 is plus 6. And that's also true. Log base 10 of 10 equals 1. So yes, they're both true. And both solutions work. 5 and negative 2 are both solutions. Okay, the second one, what's our first goal? Goal number 1 is to isolate. We always have to isolate the expression we're interested in. And the expression we're interested in is isolating the log base 5 of 2x. So we have to get that by itself. And to get it by itself, you're just going to do some standard algebra. So this thing is being multiplied by negative 3 and added by 6. So what do we do first? Subtract the 6. And that leaves us with negative 3 log base 5 of 2x equals negative 6. Now, it's not obvious that the first thing you needed to do was subtract the 6. Maybe some of you were tempted to divide the negative 3 or add the 3. I mean, this all boils down to algebra. And the best way to remind yourself how to do algebra correctly is to do the story of x. So what's happening to x? X is being multiplied by 2, plugged into a log expression, being multiplied by negative 3, and then being added by 6. So subtracting by 6 is the first thing to do. Now we'll divide by negative 3, and that gives us log base 5 of 2x equals 2. And so now we just have our logarithmic expression isolated. We can convert into exponential form. So left to the right equals middle. 5 to the power of 2 equals 2x. And that's 25 equals 2x. And dividing up the 2, we get x equals 12. Why did I divide by negative 3? Well, this log expression right here, what's the relationship between it and the negative 3? This log, this thing that we boxed up that we want to isolate, it's being what by negative 3? It's being multiplied by negative 3, so you divide off the negative 3. Now, folks, watch closely here. Sometimes when you're looking at a complex expression like this, you can get lost in the details. So look at this log base 5 of 2x. We want to isolate that. So just for a moment, convince yourself how to solve a simpler problem. Does everyone agree that these two problems are essentially the same? 6 minus 3 times something equals 0. 6 minus 3 times something equals 0. Is this the same equation?
Yes.
I've just replaced the log base 5 of 2x with a y. So now I can just remind myself, just focus on the algebra. How would I solve for y here? So Jennifer, thanks for volunteering. How would I solve for y here? Subtract the 6, and then what? Exactly, divide by the negative 3. Yeah, so if you can convince yourself what to do in a simpler context, then that will remind you what method to use in a more complicated context. I do that all the time. I'll take something nasty looking and make it look easier, remind myself how to do it, and then go back and do it in a more complicated scenario. Okay, so if I plug that in, does it work? 12.5 times 2 is 25, log base 5 of 25 is 2, and 3 times 2 is 6, and 6 minus 6 is 0. So it works. All right. So this is cut off a little bit by my board here. This is 9/8 log base 3 of something equals 10. So what should we do? What's always our first goal? Isolate. We want to isolate the logarithmic or the exponential expression. You'll notice that whether you have an exponential equation or a logarithmic equation, the first thing you want to do is isolate the log or the exponential. So there's our log. It's being multiplied by 9/8. What's the quickest way to get rid of that 9/8? The reciprocal. So we multiply both sides by 8/9. And I write it in such a way that I can put the 10 over 1 and have two fractions already ready to go to multiply next to each other. Over here they cancel out, and I have log base 3 of something equals 80/9. And so that's just a logarithmic expression, and we convert it to an exponential expression. Left to the right equals middle. 3 to the power of 80/9, whatever that is the answer. 3 to the power of 80/9. I would like to order 3 to the power of 80/9 pizzas, please. Now, just off the top of your head, folks, see, one really good skill in math is just estimation, pure estimation. If you were just to eyeball it, just like pure eyeball it, well, how big would you say 3 to the power of 80/9 is? Without a calculator, you might look at that and be like, I don't know. I don't know. But give it a guess. What's 80 divided by 9, roughly? I mean, what do you wish 80 was? 81, right? So 81 divided by 9 is 9. So let's just say that 80/9 is a little less than 9. So now what's 3 to the power of a little less than 9? So 3, 9, 27, 81, 243 times 3 again. Well, 243 times 3, I'm not sure. So I'll do 240 times 3. Better yet, I'll do 250 times 3, because that's easy. So now 250 times 3 is 750. So that's $7.50. Times 3 again, that'd be like $22. And then times 3 again, oh no, I lost myself. That was $7.50. So now that's $2,000 roughly. Times 3 again is $6,000. Times 3 again is $18,000. So I'm just saying, roughly speaking, that's $18,000. Now, I just want you to see, do you see how much I just kind of approximated and just kind of willy-nilly that? So I said 3 times 3 is 9, times 3 is 27, times 3 is 81. At that point, 81 times 3, I could just say 80 times 3 is 240. Now I'll call that 250 because that's a quarter. So 250 times 3 is 750. 750 times 3, 7 times 3 is 21. A little bigger than that, I'll call it 22. And then, where am I at? That's 1, 2, 3, 4, 5, 6, 7. Times 3 again would be 6,600. That's 8 of them. So now one more time, 66 is really 7. 7 times 3 is 21,000. Oh, well, I got a slightly different answer that time. I'm not sure, you know. So one way I did it was 18,000. Another way I did it was 21,000. What am I saying the answer is roughly? Around 20,000, right? Depending on how you approximate it, you should get an answer of around 20,000. So everybody, type that into your calculator now. 3 to the power of 80/9. The actual answer was 17,421. What's my point? You can at least ballpark it, or get in the ballpark of what the answer should be in your head by playing around with numbers and doing some approximations. You might say, Mr. G, thank you for telling me that. I'm never going to do that in my life. I'm just going to get out a calculator. Thank you very much. And that's fine. All right. We have one more to try, a couple more to try, actually, and now it gets interesting. Now it gets interesting. You can be sure to have something like this on the test. Number 8 here. We have log base 3 of x minus 4 plus log base 3 of x plus 4 equals 2. Now what do? We have two logs, we're adding them together. They are the same base. So can we just combine them? Well, do we have a rule for adding logs? We do have a rule for adding logs. And so log A plus log B is equal to log AB. So how would I rewrite this now? You can add logs as a product. So it's going to be log base 3 of bracket x minus 4 times x plus 4. How does everyone feel about that? We just used the log rule. Maybe you want to write it down nearby. Log A plus log B equals log AB. That's the rule we just used. It's a log property. So we are able to combine those two expressions together. Oh, this equation is so easy once you see the whole solution. See, like you start by looking at the original and you're like, oh, that looks pretty complex. But then you do a couple of chains of logic and then you're already at the answer. So what do we do now? We have a log. The log is isolated. We have log base 3 of this equals 2. What do we do? Anytime you isolate the log, you convert. So let's convert to an exponential. So now we have left to the right equals middle. 3 squared equals, and what is x minus 4 times x plus 4? Does everyone have this memorized nice and easy? That when you multiply conjugates, you get a difference of squares. If I FOIL this out, I get first x squared, outer plus 4x, inner minus 4x, those cancel. And then minus 16, x squared minus 16. That's a classic difference of squares. Recall difference of squares via x squared minus a squared. That's really x plus a, x minus a. So the fact that they gave us x minus 4 times x plus 4, the implication is FOIL it out and you just get x squared minus 16. So now what? We have 9 equals x squared minus 16. Add the 16 over. X squared equals 25. And square root of both sides, x equals plus or minus 5. Now let me challenge you. What do you think that means the graph looks like? What do you think that means the graph looks like? We have one x-intercept over here at 5, right? And then we have another x-intercept over here at negative 5. Do you think that means that our graph will be symmetric? We just saw a graph a second ago that was symmetric. It went through. So do you think that maybe this graph is also symmetric? I don't know. I'm not telling you it will be. I have no idea. I haven't graphed it yet. But it's just something to always think about, to always be thinking graph versus equation. What does the graph look like? What does the equation look like? So let's go ahead and try it. This equation was, oh, now I can't do log base 3. So I'm going to have to just do log, because that's the best I can do, and just trust that it doesn't change anything fundamental about the graph if I do log base 10 instead of log base 3. And so what does our graph look like? Oh, is the graph symmetric? It's not symmetric. It doesn't have a left-hand side, does it? So what does that mean? Maybe it means the negative 5 doesn't actually work, which we would know as soon as we finish the problem, right? So we got 2 answers, x equals 5 or negative 5. We haven't checked them yet. So let's plug in and see what we get. If I plug in 5 into the original, that gives me 5 in the original. Log of 5 minus 4 is 1, plus log of 5 plus 4 is 9, should equal 2. Well, is this right? That log base 3 of 1 plus log base 3 of 9 equals 2. Well, log base 3 of 1, that's 3 to the 1 equals 1, that's 0. 3 to the 1 is 9, that's 2. 0 plus 2 equals 2, that's true. So that worked. 5 is definitely a solution. What about negative 5? If we plug in negative 5, immediately it's false, because log base 3 of negative 5 minus 4 is negative 9. And we don't have to go any further. Can you log a negative? You can't. You can't log a negative any more than you can square root a negative. So that is not a solution, and therefore our graph was not symmetric. It only had one side. All right. Folks, what a good problem. What a good problem. We got to graph it. One of the solutions was extraneous, EXT, extraneous. We got to use a difference of squares formula. Like, ooh, what a good problem. Rich and full of lots of different details. I almost tripped, but I didn't. All right, so we just have a couple more problems, and then we'll switch to applications. Let's go ahead and take a break. My phone just went off. So, oh, thank you, sir. It's 9:03. Everyone be back at 9:13.
Yes.
Because the next few problems are very problems.
Yeah, so you would have natural log, and you have c to the fourth on top, and b cubed on bottom, and a squared on bottom. And then you typed in all those numbers, so c to the fourth, c is 5, so that's 5.5, yeah. Then b cubed is 8, wait, b cubed is 27, and then a squared is 4. So you have 625 divided by that. So, yeah, so natural log 1.75586. So you're the following. How strange. Hold on. I mean, it's not unheard of that this thing just sometimes has errors. And there are no specific instructions.
B2.
It didn't work.
The other, like where you
Yeah.
put the B over the top, or and C.
And what, it didn't work? It also didn't work. I wonder why on earth. I mean,
In this question, rest of that.
oh, how nice that you can just scroll through. I mean, they're just separating it all out, which is so needless. You can just evaluate it where it is. Oh, and they're saying if they're equal to something. How do we go back? Oh, ln of a is equal to 2. It's not that a is equal to 2. ln of a is equal to 2. Now that makes sense. We do have to take that whole expression and expand it. You know what? I bet I did all of those wrong with you guys. I bet I did.
Yeah.
Okay, that
So you
explains
have to
it.
expand that. Okay.
Where did they have that problem? Oh, it's right there. Silly me. That's what it was. Yeah, so these would have to be expanded. Okay, let me consider whether or not we even need to include these, and I might just take them out.
Okay.
Thanks for pointing that out.
Yeah. That makes sense.
Hey. Yeah, let's just talk about class. Thanks.
He took offense to that. I don't know how to speak it. Come back, folks.
All right, we have a couple more really exciting log equations to solve. And I think we all essentially see the essence of what we're doing, which is to isolate the log and convert to exponential. Like, perhaps you want to write that down somewhere. That the heart of what we're doing is to, step one, isolate the log, and then step two, convert. All right? That's what we're trying to do. Now, in this particular case, these next few problems, it's a little more complicated because there are multiple log expressions. But that's okay, we're just going to combine the log expressions using log properties. So, for instance, in this first one, we have log 169 3 raised by 7 minus log 169 5 raised by 9 equals 1/2. The fact that we're subtracting two logs, what log property are we going to use? Yeah, the quotient rule. So log A minus log B is actually equal to log A over B. So that's the one we're going to use. And this really highlights what math is like. To be in a math class or to study math, you have to constantly be thinking, what rule can I apply? What rule can I apply? What rule can I apply? Like a second ago, we did the difference of squares formula. Like, that was kind of out of the blue. And in situations like this, we have to be thinking, what rule can I apply? This one, this log property. So we go ahead and combine these expressions. So now we have log 169, which is super random. Although it's not that random. Does anyone recognize the number 169 as your old pal and friend? 13 squared. Okay, so we have log 169. Now we're going to divide. So that's 3x plus 7 over 5x minus 9 equals 1/2. All right, so we applied the quotient rule for logs. And now we just have this rather unfortunate looking thing. Like, you look at this and you think, it's a rational expression. There's a vertical asymptote there. 169, kind of a big number, but it's just 13 squared. 1/2. You know, it's a power down fraction. And yet now, going back to our essence here, isolate the log and convert. Now what happens when we convert? 169 to the 1/2? What's 169 to the 1/2? That's just the square root, right? There isn't something to the 1/2, it's just the square root. So the square root of 169 is just 13. Plus or minus 13? That's a good question. Is it plus or minus 13? Is it plus or minus 13? Yeah, this was part of the formula itself. So we would tend to say that that would just be a plus 13. Although I'm a little on the fence right now because I think, well, you know, it wouldn't hurt to keep track of both the plus and the minus and then check both ways and see what solutions you get. Because ultimately, what's our end game? Find a value for x and plug it back into the original and see if it works. So when you're not sure, it doesn't hurt to keep both. I'm going to keep both. It's plus or minus 13, which is really going to give us two separate equations. So on the one hand, what are we doing over here now with this rational expression? We want to solve for x. I want to remind you how to walk your way through something like this. You might look at this and say, oh man, it's a fraction. How do I solve for x? What do I do? Well, what's the most inconvenient part about this fraction? The denominator. What's the most inconvenient part of any fraction? The denominator. How do you get rid of a denominator? Multiply it on both sides. Multiply the denominator on both sides. So now we're going to go ahead and multiply the 5x minus 9 over to both sides. And so now I want you to notice what I'm going to do here. I'm just playing it safe. If the answer was positive 13, I'd have 13 times 5x minus 9 equals 3x plus 7. That's one reality. Or if it was including the negative 13, I'd have negative 13 times 5x minus 9 equals 3x plus 7. Again, I'm just not super sure yet. You know, I'm kind of, you know, unsure. Am I supposed to do the plus or minus? Am I not supposed to do the plus or minus? So I'm just going to follow both ways and see which way leads to the answer that I can plug back into the original and make it true. Right? So you're just playing it safe right now. So now we distribute. 5 times 13 is what? 65x minus 9 times 13 is what? 117 equals 3x plus 7. So let's solve this equation on the left first. After all, we were kind of thinking that it was positive 13. So then what? I subtract 3x from both sides, and then I add 117 to both sides. Did I do that multiplication correct? Did anyone check me? So 13 times 5 is 65, and 13 times 9 is 117. Okay, good. So then we minus the 3x over to this side, and that gives us 62x. And then I add the 117 over to this side, and that gives me 124. Oh, okay, great. 62x equals 124. I divide both sides by 62, and what do you get? X equals 2. Okay, so that was if the square root of 169 is just 13. What if it's a negative 13? I'm just doing this now to be cautious. This is negative 65x plus 117 equals 3x plus 7. And so now I minus the 3x, that gives me negative 68x. Then I minus the 117x, so 7 minus 117 is negative 110. And ooh, this looks terrible. X equals 110 over 68, which is 55 over 34. Kind of doubting it. But, you know, who knows? We don't know yet until we plug it back in and see if it makes it true. Wouldn't we all be surprised if 55/34 was really a solution? I'd be surprised. Okay, so now we either have the answer 2 or we have the answer 55/34. And so what do? Just plug it back into the original and see if it makes it true. So I'm going to plug in the 2 first because I'm feeling a lot better about that solution. So I'm going to check. And on the left-hand side, I have log base 169 of 3 times 2 is 6 plus 7 is 13. Minus log of base 169 of 5 times 2 is 10 minus 9 is 1. So sure enough, 169 to the what is 13? That would only be if 169 got square rooted, which is raising it to the 1/2. So that's 1/2. And then 169 to the what equals 1? 0. And so 1/2 minus 0 is 1/2. So that worked. 2 is definitely one answer. 2 is definitely one answer. Now, keep in mind, you could do this on your calculator. Log base 169 of 13 minus log base 69 of 1. You type all that into your calculator, and you would get 1/2 equals 1/2. So how about this other terrible thing, 55/34? So log base 169 of 3 times that, so 55/34. So times 3. I'm going to do all this on my calculator, plus that. So that's log base 169 of that. So log of that divided by log of 169. The left-hand side so far is 0.48 minus, and then I have 55/34. So I'm plugging in 55/34 in my calculator to see if it works. Oh, it doesn't work. That's convenient. Oh, it doesn't work because it leads to a log of a negative number. And therefore, that's not possible, therefore that's not possible. So yeah, it turns out we did not actually have to do the plus or minus from the square root from 169 to 1/2. We only did the plus, which is consistent with what we formerly said, that if the square root is part of the problem itself, It's not plus or minus. It's only plus or minus if you're doing an action step, which means you're square rooting both sides. Okay, so we're done with the problem. Here's 2. The answer's 2. Okay, how about this next problem, number 10? Now let me just ask you, since all of those have log base 7 in it, is anyone tempted to just drop all the log base 7s and just write down 2x equals 2 plus x plus 12? Is anyone tempted? It's totally wrong. So don't do it. It's a temptation. You might think, hey, that'd be nice. No. We can't do that. We have to think about what we're allowed to do. We can't just drop all the logs. So what are we allowed to do?
Okay, you want to divide everything by 2 on each side, so now.
You mean to divide that up?
Yeah, because I'm looking at it, and then after that, then your base is all the same.
Well, the bases are already all the same. If I divide everything by 2, then I'd have a 1/2 in front of that and a 1/2 in front of that. That'd be a little unfortunate. What log property can I use right now? Can we add 2 logs together? How does the property work? How do you add 2 logs together? You just do the log of the product. So now this right-hand side becomes log base 7 of 2 times x plus 12. So that's 2x plus 24. What about over here on the left-hand side? What's another log property I can do with the 2? Yeah, I can bump that 2 up to become an exponent on the x. So now on the left-hand side, I have log base 7 of x squared. Yeah, so first of all, notice how we just used 2 log properties. So we use the power rule and we use the product rule. And now both sides are log base 7, and you can drop the log base 7s. We're not really dropping the log base 7s. We're using a sophisticated argument which states that if you can equate the logs, you can equate the arguments. Since this is log base 7 and this is log base 7, whatever is underneath my hand right here must be equal to each other, and therefore x squared must be equal to 2x plus 24. So we're not just dropping the logs. That would not be the right way to say it. We're stating in a logical way that the log base 7 of this equals log base 7 of this, therefore this and this must be the same, and therefore we can equate them. And then what do? Move everything to one side. Anytime you just have a polynomial, you want to move all the terms over to one side so that you can have a chance to factor it. So we have x squared minus 2x minus 24 equals 0. And what multiplies to make 24 that adds to make 2? Is it 6 and 4? X minus 6, x plus 4. And so by the 0 product rule, we have x equals 6 and x equals -4. And at this point, folks, I hope that you're really on edge. Like in a good way. I don't mean in a bad way. I don't wish you to be unwell. But I hope you're on edge about that 6 and the -4. I hope that you at least now have a healthy skepticism. Like, no, wait a minute. Is the answer really both of those? Because one of those, if I plug it in, maybe it's not going to be true. In fact, maybe neither of them are true. Maybe both of them are true, right? So like, even though we just did a whole bunch of really great healthy algebra, you're now left with more of a combinatorial process. Like, well, is the answer both 6 and -4? Is the answer only one of them? Or is the answer neither of them? There's this whole extra process that you do at the end of algebra where you plug in the numbers and see if it works. So let's try plugging in 6. 2 log 6 equals log 2 plus log of 6 plus 12, which is 18. Is that a true statement? We find out if it's a true statement using the same 2 log properties we used to start the algebra. The 2 can bump up on top, so that's log of 6 squared. And here we can add these logs together by multiplying the arguments, so that's log of 36. So now I have log 36 equals log 36. Which is true. So definitely 6 is correct. -4, is it correct? I don't know. I hope, again, that I've left you feeling at least a healthy skepticism at the end of every algebraic process. You don't really know that's the answer yet until you plug it in. So now let's plug in -4. 2 log -4, and I can already stop. Right, because you can't log a negative. So -4 is an extraneous solution. The algebra took us there, but it's not actually true. And you can all cross out 11 and 12. I think we've covered a good healthy dose of solving exponential and log equations. I'm sure you all had wonderful dreams about logarithms over the weekend. And now you can all continue to think about solving logs. All right, that brings us to section 6.5, which is applications. You know, in any section that you do, anytime you start a new chapter in a math book, they're going to give you lots and lots of definitions, right? They tell you what a log is, how to convert it from log form to exponential form. You learn all these log properties. But really, there's two main activities you do in mathematics that are actually important, that actually make the world go round. One is solving for an unknown. You know, solving an equation, solving for an unknown. That's a fundamental activity that humans do in all industries. You solve for an unknown. And then the other is word problems. Everybody's favorite thing is a word problem. Because that's what life actually is. Life is a word problem. So we built up all the skills that we have now from section 6, 1, 2, 3, and 4, just so that we could look at some word problems and figure them out. So I really hope to convince you that this is the exciting part. This is the really exciting part now, that you can read a word problem and understand it and try to solve it. You know, that's what makes you sophisticated, right? That you could read a word problem and figure it out. So let's take a look. They're starting us off here with a couple formulas. They're talking about compound interest. You've probably seen the compound interest formula before. There it is, the P times 1 plus R over N to the NT. We're going to use that formula a few times. And that's discrete compounding. So notice it says of initial principal P, so that's how much money you want to invest, at an annual rate R, and the interest is compounded N times per year. Let's just talk about that real quick. What does it mean to compound interest? Let's do an example. Let's say that you invested your money at a bank, and they're going to compound your interest 4 times per year. Here's an example for you. So let's say you're getting 8% interest, which is ridiculously unheard of. Nobody gets 8% interest at a bank right now. What's the interest rate at a bank right now for a savings account? Maybe 1%? What does someone say? Yeah, not much. Maybe you're getting 1 or 2%. Well, let's just pretend that you're getting 8% and that you're compounding it quarterly. Compound quarterly, which means N equals 4. Now this is really interesting. Okay, so compounding, the definition compounded quarterly, what that means is that 4 times a year, they're going to give you a little interest, right? So you stick that money in the bank account, and 4 times a year, so quarterly, right? So January, February, March. At the end of March, they'll give you some interest. April, May, June. At the end of June, they'll give you some interest. July, August, September. At the end of September, they'll give you some interest. And then October, November, December. At the end of December, they'll give you some interest. So what does compounding mean? Compounding is one of the best words that you can possibly think of. Bank gives you money. That's what compounding means. Bank gives you money. Unless you're talking about credit cards. If you're talking about compounded interest on a credit card, then who's getting the interest? The credit card company is getting interest from you. Now, just to share with you how terrible the world is, and it's not really terrible, I'm just, if you put money in a savings account, they're probably going to compound it quarterly, maybe monthly, right? So you get interest 4 times a year, maybe 12 times a year. Do you know how often your credit card interest is compounded? Do you know how often they compound your interest on a credit card? How many times per year are they making you pay interest on your credit card? It's daily. Credit cards compound interest daily. Every single day you keep a balance on your credit card, every single day, a little interest from you, right? So again, compounding means computing interest. So if you're saving money in a savings account, they're going to give you interest quarterly, 4 times per year. If you keep money on a credit card, they are compounding interest daily, which means every little day they're tacking a little bit of interest onto your total amount due, right? That is unless you pay it off at the end of every month, right? If you pay your credit card off at the end of every month, you owe no interest at all. But the minute that you don't pay your credit card off at the end of every month, they go back and look at all the interest that they were charging you every single day. They add it all up and they add it onto your bill. All right, so that's how credit cards work. So what does compounding mean? Interest. So In the case of compounding interest, the way it really works is you're getting 8% on your savings account, but they're compounding it quarterly, meaning every quarter they're going to give you some interest. They actually take that 8% and divide it by 4, and then you actually get 2% every quarter. So at the end of March, they give you 2%. At the end of July, they give you 2%. At the end of September, they give you 2%. And at the end of December, they give you 2%, which overall is actually going to end up giving you a little bit more than 8%, but that's how they actually do it. So now you all know what compounding discretely means. A discrete compounding means quarterly, monthly, daily, weekly, some finite thing. Whereas continuous compounding means they compound the interest every second, every fraction of a second, every microsecond, every picosecond. They're taking a little bit of interest. It's not like the interest only comes in March and then in July and then in December. The interest is just a tap of water. Like you turn on your bathtub and the water is just flowing. That's what continuous interest means. The interest just flows nonstop like water from a faucet. And that's continuous interest. Meaning, if you were getting continuous interest on your savings account from a bank, you could just pull up your bank account online and look at the total, and you should see a running total of, let's say that you put $1,000 into the bank account. Then if they gave you enough decimals, you should be able to see these decimals just changing fluidly and constantly as they're putting money into your bank. That's compounded continuously. So compounding discretely means you only get interest n times per year, and it's n separate events. Compounded continuously means it's like a flow of water from a faucet, and the money is just flowing. Well, I don't know. I mean, even the stock market is jerky movements where they just look at the end of each day. So I mean, the stock market's changing all day long, but really all that matters is what happens at the end of the day. I don't know. Your question is a complex one. Okay, so now, everybody, I hope that you have the concept down. Let's go ahead and try a couple problems. So it says here, find the amount A in the account as a function of the term of the investment, T in years. That just means write down the formula. Determine how much is in the account after 5 years and after 10 years. And then determine how long it will take for the initial investment to double. All right. Everybody ready? Let's look at our first situation. $500 is invested into an account which offers 0.75%, that's more realistic, compounded monthly. So first of all, if it's compounded monthly, how many times per year is that? Yeah, then it's 12. And if it's 0.75%, we always write our interest rate as a decimal. What's 0.75% as a decimal? 0.0075. Right, because you move the decimal twice to the left to convert a percent into a decimal. And then finally, the 500 is our principal. That's how much money you're investing. The first thing you always want to do is identify the information. So let's take a look here. Since it is compounded monthly, not continuously, we're going to use the first formula. And our first formula states A equals P 1 plus R over N to the NT. One thing I like to do is just list out those things. A equals, P equals, R equals, N equals, T equals. I'm going to just keep track of what we know. So what do we know so far? We know the principal is 500. We know the rate was 0.0075. We know the N was 12. And T, what are they telling us to do? Determine how much is in the account after 5 years and 10 years. Just for the sake of time, let's just do the problem for 5 years. So, do you all see what they gave us? This is a very important activity right here. I would always do this for any money problem. I would just list out the variables that are in the formula. You'll notice I listed them in the order they are, A, P, R, N, and T. And I just write down what I know. And since I know I'm investing $500 at 0.75% interest rate, and I'm getting compounded interest 12 times a year for 5 years, what's obviously the thing we're trying to find out? A. We know everything else, we don't know A, so obviously we're trying to solve for A. And in fact, that's what they're asking us to do. Find the amount A in the account as a function of all those things. So let's go ahead and plug everything in. We have A equals 500 1 plus 0.0075 over 12 to the power of 12 times 5. I'm going to tack on a few more notes here. Really important that you remind yourself that the rate always has to be a decimal, not a percent. It has to be decimal. N is always the number of times per year. So in this case, 12 times per year. Month is 12 times per year. And T is always in years. Not months, not days. T is years. Okay. This formula, though you could type the whole thing into your calculator all at once, that's very dangerous. I would compute the inside and compute the exponent. So I'm going to do 0.0075 divided by 12, add the 1 to it. That gives me 1.000625, all raised to the exponent of 60. That expression right there is really interesting. I can't help but share it with you. Because we're getting compounded monthly, see, the 0.75% is the yearly interest. That's the yearly interest. How much interest are you actually getting each month? That much. The actual amount of interest that you get each month is 0.06%. So that's the actual compounding of the amount of interest you get. And how many times are you actually going to get that interest? Well, you're doing 12 times a year for 5 years, so how many times do you get interest? 12 times a year for 5 years, how many times do you get interest? 60. So that's the actual number of times you get interest. So just by simplifying this formula, you're actually getting some really interesting information. This formula now tells you that I invested $500 and that 60 times over the next 5 years, I'm going to get that much interest on my account. Okay, so now you can type all that into your calculator, I think risk-free, 500 times 1.000625 to the power of 60, and you get the actual answer of $519.0999, that's 10. So $500 is invested, compounded monthly for 5 years, and at the end of 5 years, you got 19 bucks to show for it. 19 bucks after 5 years. All right. Now that problem is not done. We've done part A, which was to simply write down the formula. So this was part A. We wrote down the formula. And then part B was determine how much money is in the account. That was part B. We actually computed it. So now part C, it says, how long will it take for your money to double? Now, first of all, if it took you 5 years to make 20 bucks, how long is it going to take you to make $500? You'll be dead. I will all be dead. Your kids will be dead, your grandkids will be dead. Like, we're talking a long time from now for this money to double. Sorry, I didn't mean for that to sound terrible. I'm just saying, it's a long time into the future, right? Like, what do you think? Are we talking 100 years, 200 years? I mean, it's going to take a long time to double your money. So, we want to be able to ask the question. Now remember, go back in your mind. Every word problem, there are only 2 things that you do in a word problem. Let's say you have a function, they give you a function, the function's x squared minus 20, and then they give you the number 500. What are the only 2 possible things you can do with the 500? You either plug it in or make it equal, right? There's only 2 things you can do in a word problem. You either plug it in or you set it equal. Now what did we already do? We already plugged in all the numbers. So now what are they asking us to do? Set something equal. So let's come over here. Our formula is, now notice they're saying, how long will it take? Therefore, what are we solving for? A, P, R, N, or T? T. We're asking how long will it take. So let's write down the formula again with the variable T. So that's 500, 1 plus 0.0075 over 12 to the 12T. Very important that now T is the only unknown. So here's our formula. The only thing we don't know is t. And actually the a, what do we want the a to be?
Household.
Yeah, we want to double our money, so we want the a to be 1,000. All right, so that's what we're doing. On like a big picture scale here, I want you to notice, in this problem, the only variable left was a, because we were solving for a, and we plugged something in for everything else. You can only have one variable at a time. So now in this problem, we did plug something in for a, and now the only variable we have is t. So in this problem, we're solving for time that will double your money. In this problem, we were just solving for the amount that we'd have at the end of 5 years. Okay, so now what do? We have this equation. We want the amount to be double. So now we need to solve for t. Where's t? In the exponent, and therefore, what will we need in order to solve for this variable? A logarithm. Because anytime you solve for an exponent, it's a logarithm. Okay, so let's start doing our work here. We've got, just to simplify the inside of the parenthesis, we already know what the inside of the parenthesis is. It's 1.000625, all to the power of 12t. What do we do? We want to solve for the exponent. What's always our first goal? We need to isolate the exponential. We always need to isolate the exponential or isolate the log. So what do I move over first? I can divide over the 500. That gives us 2 equals 1.000625, all to the power of 12t. Notice that 2. That 2 is important. That 2 represents the fact that we want to double our money. What if we wanted to triple our money? What would I change the 2 to? A 3. And if I wanted to quadruple my money, I would change the 2 to a 4. So that's really symbolic. That number that we ended up there, it's not a 2 by accident. It's literally now asking the question, we want to double our money. Okay, now we've isolated our exponential. What do you do after you isolate the exponential? You're going to convert. Convert from exponential to log form or convert from log form to exponential form. We're already in exponential form, so let's convert to log form. So that'll be log base 1.000625 of 2 equals 12t. Now, if it helps you see it better, instead of 2 equals this to this, you can put the 2 over on the right-hand side, so it's a little easier. Remember, the first number always stays first, so it's log base that number of 2 equals 12t. Now, what do you do with this log base 1.000625? Sorry, 0.00625. 0.00625. How do you calculate that? On your calculator. And I hope you all have that muscle memory now that you just do log 2 divided by log 0.1000625. So let's all compute that. Log 2 divided by log 1.000625. That gives me a very big decimal, 1109.382026. I'm going to keep all those decimals. You always keep all decimals throughout the whole problem. You only round at the end. So now we divide by 12. Now remember, folks, we're solving for time. At that point, that'd be 1,109 years. Thank goodness we're dividing by 12. So now how long is it? Time equals all that divided by 12. Okay, 92. 92.448. So we'll call that 92.45. 92.45 years. Hey, we might not be alive, but your kids will. So I was a little pessimistic in the beginning. So it'll take 92 years for your money to double. Now, folks, to be honest, if that was a little tricky, which I don't doubt that it was a little tricky, what we should do is do that again. So you feel comfortable with it. And that's probably why they told us to do it for 5 years and to do it for 10 years. So if I were you, right now, I would take out maybe a separate sheet of lined paper. And let's go ahead and work our way through those same 3 problems again, just to really lock it down in our memory of what we just did. So I'm going to do that whole problem again, but for 10 years. So the part A says, find the amount in the account as a function of time. So always, you start by writing down the formula. So my formula is A equals P, 1 plus R over N to the NT. And they want a formula in terms of T. So again, I'm going to remind myself, A, I don't know, P is 500, R is 0.0075, N is 12, and T, well, the first thing they want is just for us to write it down as a formula. So the first thing I'll do is just write down the formula that the amount of the bank is equal to 500 times 1 plus 0.0075 over 12 to the power of 12t. So that's just a formula. If we wanted to clean that up a little bit, we'd say the amount that I have in the bank is 500 times 1.000625 to the power of 12t. That's technically the answer to part A. Right, because you might have a problem on more that just asks, what's the formula? It's just a formula. You took the original formula, you plugged in the things you knew, and now the only thing that you'd have to do left is either plug in the number of years that you're waiting, and that will compute for you how much money you have. Or you plug in how much money you want to have, and then solve for t. Right. So notice that this formula lends itself to two different questions you could ask. You could ask, how much money will I have in 10 years? You just plug in 10. You could ask, how many years do I have to wait until I have $1,000? And you plug in 1,000. And that's how all word problems work. You're going to end up with a formula that has probably two variables, and you plug in for one of them to solve for the other, or you plug in for this one to solve that. All right, so everyone has part A? So what was part B? Determine how much is in the account after 10 years. So part B, I'll just plug in 10. So A equals 500, 1.000625 to the 12 times 10. And you can type all that into your calculator. Since that's really just 500, 1.000625 to the 120. And again, as a quick look, what does that mean? It means you're investing $500, and over the course of 10 years, they're going to give you interest 120 times. 120 times, that is once a month. You're going to see a little more money in your account. And how much interest are they giving you every month? That much interest, which is really 0.0625%. So now we type all that in, 500, 1.000625 all to the power of 120, and we get $538.93. Did this problem say to round to 2 decimals? Round to the nearest cent. Yeah, round to the nearest cent. All right, so now here's the exciting part. How long do you have to wait to double your money? So again, notice, this was our formula. A equals 501.0625 to the 12t. And now they're asking to double the money. So what do we put in for A? You want the amount of money to be doubled, so what do you put in for A? 1,000. So we write down our formula as 1,000 equals 500, 1.000625 to the 12t. And we're solving for t. Therefore, t is still in the equation. We're solving for this t variable. That t variable is in the exponential, or it's in the exponent. Therefore, you know you'll need to use a logarithm to solve this problem. This is definitely a problem on the test, on the practice test, on your final exam. The next job interview you have, they're going to ask you this question. No, I'm just kidding. Maybe I'm not. Okay, so what do we do first? Isolate the exponential. So we're going to divide off that 500. Again, by dividing off the 500, we get 2, which is still asking the question, I want to double my money. So 1.000625 to the power of 12t. Now, of course, we already did this problem. We're just This is the exact same problem we just did, but it doesn't hurt to do it twice because it builds muscle memory in your mind, so you remember what to do. This is really, I'm going to put the 2 over there. I always like to have my exponential on the left equals a number. That's just what I prefer. I see it better that way. So now that would be log base 1.000625 of 2 equals 12t. Now using the change of base rule, we can type that into your calculator. So that's log 2 divided by log 1.000625, which is still 1109. This is the same problem. Then I keep all my decimals and then divide off 12. Okay. Since I have the whole problem over there, I'm going to erase this to give me more room to do number 2. So even if you could double your money in 92 years, you have a very short time period to use that money. All right, so number 2, it now says we're going to invest $5,000 into an account which offers 2%, 2.125% compounded continuously. So now what changes is the formula that we're using. Since it's compounded continuously, now we're going to use the other formula, which is A equals P e to the RT. Formula I just always call PERT. PERT. You remember that PERT Plus shampoo? Do you remember PERT Plus shampoo? It was green. Did any of you use PERT Plus shampoo? I used to love PERT Plus shampoo. Do they even sell it anymore? No, there's no room in the economy for green shampoo, is there? How strange. All right. So now what? Part A, find the amount in the account as a function of time. So we have 4 variables here. A, P, R, and T. Again, I would always start by doing this analysis. Write down your givens. Be organized in your thinking. Write down your givens. Now, what do we know? We're investing $5,000. That's my P. The interest rate is 2.125%. So that, turn that into a decimal, that's really 0.02125. And you'll notice A and T are the 2 things we don't know. If I plug in the number of years, I'll be able to calculate the amount. If I say how much I want to have, I'll be able to calculate the time I have to wait. So there's a nice little relationship here between T and A. So part A simply wants the formula. So I'm going to write down here, part A simply wants the formula. So A equals 5,000 e to the 0.02125. That's it. Part A just says write down the formula. So again, think about what's happening in this problem. The interest is compounded continuously. So it's like the bank has just turned on the flow of money into your account, just like water from a faucet, and they're just pouring money into your account. So if you were able to look at your bank balance and see enough decimals of accuracy, you would just see those decimals ticking and changing, just like seconds on the clock. You'd just be continuously getting money all the time. Okay, what's part B? It says how long, determine how much is in the account after 5 years and 10 years. So you can do both of those problems. So A equals 5,000 e to the 0.02125 times 5. I know I'm attempting to alter and change a lot of your behaviors. Use more parentheses, show more work, all these things. I'm trying to parent you. These are just best practices. These are best practices. I really recommend that at this point, before you plug that into your calculator, you would just compute the exponent. So this 5,000 e to the 0.02125 times 5. Now that's just 0.1065. Little baby steps. Okay, so now you can type that into your calculator, no problem. 5,000 e to the 0.1065. I got $5,560 and 0.4999, that's 0.50. Did anyone else get 55, 60, 50? Take the silence as a yes. Then you all type that into your calculators and confirm the same answer. Now, hey, at the end of 5 years, now how much money did you gain through interest? How much extra money did you earn from interest? $560. That sounds better than the $19 from the previous problem. I want to make $560 for free. Of course, that took 5 years, so 560 divided by 5, that's just over $100 a year. I'll take it. Any one of you want to just come up to me and hand me $100 every single year, I'm fine with that. I will take it. I will never turn you away. No. 100, only 100? No, keep it. No. I would always take $100 from each of you once a year. Hint, hint. Okay, so now what? I'm not going to do the second part with you. You can all plug in 10 separately and get your own answers. So let's go to part C. We want to know, how long will it take to double your money? So what does it mean to double our money? Again, if I write out the formula, A equals 5,000, e to the 0.02125 t. I have two different variables here, and I'm wanting to double my money. So what do I put for A? 10,000, because I want to double my money. Instead of having $5,000, I want to have $10,000. Now, what do you think? Are you going to be able to enjoy this money while you are still young and able? Hopefully. We might be able to grab this money in our 60s, maybe. So let's find out. We want to isolate the exponential. So that thing is being multiplied by 5,000, so we divide by 5,000. And once again, we're not surprised that we get the number 2, because we're asking, we want to double our money. And so this is just an exponential. Again, I'm going to write equals 2 instead of 2 equals. I just prefer to do that. I just like to have my exponential on my left and then the number on the right. I just see converting it better that way. So now I have log base e of 2 equals 0.02125t. Of course, log base e is just ln. So now I have ln2 equals 0.02125t. And now t is being multiplied by that decimal, so t is being multiplied by 0.02125, so you divide by 0.02125 on both sides. And that gives us t is equal to the natural log of 2 over 0.02125. And now we type into our calculator. So natural log of 2 divided by 0.02125, which is merely 32.62 years. Fantastic. Most adults will spend 30 years having some sort of a career, at least, right? You start working when you're 20. I'm just ballparking it, folks. Start working when you're 20, retire maybe in your 50s, maybe in your 60s. Okay, maybe 30 or 40 years. Maybe we can all expect to work at least 40 years before you retire. Now, folks, did you notice anything interesting about the doubling formula? What did you notice about the formula that tells you how long you have to wait to double your money? What's the top part? Natural log of 2, where the 2 means double your money. And what does the 0.02125 represent? The interest rate. Do you think that we can go ahead and conclude that the time that you have to wait to double your money is always the natural log of 2 over the interest rate? As a decimal? Yeah. Yeah, that's the formula. And in fact, if you wanted to, you could even prove that that's the formula for doubling your money. And if you wanted to, even memorize that's the formula for doubling your money. Because just take a look. A equals P e to the RT. See, this is fun. I want to double my money. So if I start with P, what's double P? 2P. So I want to double my money. I divide both sides by P. And that gives me 2 equals e to the RT, and which is really e to the RT equals 2. And so then I convert to log form, so that's log base e of 2 equals RT. and log AC is natural log of 2 equals RT, and T is being multiplied by R, so divide by R, and sure enough, doubling time is the natural log of 2 divided by R. So is that a formula you can use, lickety-split? Yeah, but only for compounded continuously. If they ask you for doubling time with compounded continuously, there's just a formula. And keep in mind that R is a decimal. You can't put the percent there, that has to be a decimal. All right. See, I told you word problems were your favorite. And I realized that was a long word problem. There was a lot to think about and do there because we technically had 2 different formulas. You'll notice the processes for part A, B, and C were the same for either formula. It just depends on what formula you start with. Questions or thoughts before we move on? Now these days, can't you just Google all this? There's website calculators where you just go there, tell them how much money you want to invest, what percent, and they'll just tell you all this. So you see websites today have completely made it so that anybody can get all these answers by just Googling it, and you don't necessarily know how to do all the number crunching yourself. In fact, I'm pretty sure even bankers, you know, you ask yourself, when are you ever going to use these formulas in your life? You know, surely when I'm a banker. No. Even bankers just have a website, they type in the information, and then it just computes it for them. All right, so that's our money question. Do we have any more money questions? I hope so. Let's do all of our money questions first. How much money, no. How much money needs to be invested now to obtain $2,000 in 3 years if the interest rate in a savings account is 0.25% compounded continuously? What a great question. What a great question. It says, let's read it again. How much money do you need to invest now in order to obtain $2,000 in 3 years? So let's just stop right there. This is, what, October of 2018? And let's just say that you know for sure that in October of 2021, you need $2,000. I don't know why you'd be overly that specific in your long-term plans, but you're like, whoa, in 2021, I need $2,000. I'm going to need the $2,000. I don't know why, but you just need $2,000. So how much money would you have to invest right now today such that by the time 3 years rolls around, you've got all that money in free interest and you'll have $2,000? So how much do we have to invest today? Anyone want to just take a guess? Just ballparking, how much would you need to invest today? Maybe $1,990? You know, to hopefully make $10 in interest? I don't know. I mean, depending on how much interest they're offering us, it could be that you only have to invest $1,900 today. And that by the time 3 years is done, you'll only have $100 in free interest. You'll have the $2,000 you want. But that's the purpose of this problem. To make it a little more concrete, I have a 2-year-old and a 3-month-old, and we're asking ourselves, how much money do we want to have available for our kids to go to college? So let's just say that by the time that our kids are 18, we want to give them, you know, $10,000, which is like nothing, right, in terms of tuition in the future. $10,000 might get them a semester or 2, right? But let's just say that I wanted $10,000 for them available in 18 years. How much would I have to invest now in order that I would have 18 years of interest compounding to get me up to $10,000? And so maybe, you know, depending on the interest rate, maybe I'd only have to invest $7,000 now, today, such that 18 years from now, it grew into $10,000. And this is a practical question for all of us to ask. How much do we need to invest now so that you'll have money to give your kids to go to college? Or how much do you have to invest now so that when you retire, you have enough money that you want? So this is a very practical question. Okay, so now how do we solve it? How much money needs to be invested now to obtain $2,000 in 3 years if the interest rate in the savings account is 0.25 compounded continuously? Where do we start? You start by writing down the formula. A equals PE to the RT. That's always how you start a problem, is you write down the relevant formula. We're dealing with compounded continuously, so there it is. That's my formula. I'm going to go ahead and break this down. A, P, R, and T. What do I know? How much money needs to be invested now to obtain $2,000 in the future? So yeah, I want $2,000 in the future. How much do I need to invest now? I don't know. P is my unknown. I don't know how much I need to invest as my principal. My interest rate I know is 0.0025. I'll go ahead and convert that to a decimal. And time is 3 years. I want you to notice that everything you have written down so far, everything I have written down so far, this is called a best practice. You start by writing down the formula. You start by writing down what you know. And you already feel a little jazzed, right? Like, hey, I'm moving along. This is looking good. Looks like I know what I'm doing. I wrote things down. And it's very obvious what you're trying to solve for because it's the one thing you don't have. So now what do we do? Plug it all in. So I'm going to have 2,000 equals P e to the R T. Now let's think abstractly for a second. Is the unknown in the exponent? No, we do not have an unknown in an exponent. Therefore, do we need to use a logarithm? No. Right? Just by thinking abstractly about what we know, logarithm means the unknown is in the exponent. Our exponent is not unknown. Our exponent is very, very known. We have 2,000 equals P e to the 0.0075. E to the 0.0775. I can just type that into my calculator. So now I have 2,000 equals P times some number. E to the 0.0075. That's 1.0075. Keep all the decimals, folks. 28195. Where's the unknown? P? P's just being multiplied by a number. What do we do? Divide by the number. 1.0075, etc. Divided by 1.0075, etc. And so P equals 2,000 divided by that number. Which should still be on your calculator if you just calculate it. So you do 2,000 divided by that answer, and you get 1985.06. Ah, so how much money do you have to invest now so that 3 years from now you have $2,000? $1,985. So how much money do you get for free from the bank? Almost 15 bucks. Yep. Now, some of you might be saying, 15 bucks, what's the point? Why even bother to invest it? I'll just take my 1985, spend it now, I'll just use it to buy things, and then I'll just wait for 3 years, and then 3 years from now, I'll scrap together the money. Like, is that what you really want to do? You want to wait 3 years and then all of a sudden scrap together the money? Yeah, like, no, I mean, if you have 1985 right now, and you have it already, you might as well just put it in the bank and leave it there. Because that way the stress, 3 years from now, you don't have to be scrambling to put together the money, right? So I just want to argue that even though we're not getting a lot of money and interest, there's still a good reason to put the money into the bank. You already have it. Don't touch it. Don't spend it. Just keep it, right? Because a lot of people will say, I'm not really going to get a lot of money from investing, so why bother investing it? I'll just keep the money. But if you just keep the money, what are you going to do with it? You're going to spend it. How much of it are you going to spend? All of it. And then how much are you going to have in 3 years? None of it. So even though you're not getting a lot of interest, why should you invest the money? Because then you can't spend it. And that's a huge reason to invest money. So you don't touch it. Okay, was that a hard problem? No. Keep in mind, word problems look intimidating in the beginning. But what can you do to help yourself out? Write the formula. Write what you know. Plug in what you know. And then think, okay, how do I solve this algebraically? So let's do another problem. Well, that was it for money problems. Okay, so money is one thing that can grow exponentially. Other things that can grow exponentially are biological material. And that's what this question is all about. Biological material. Uninhibited growth. Uninhibited growth. What a phrase. Uninhibited growth. What's that? So uninhibited growth. If a population increases according to the law of uninhibited growth. Now, what does that really mean here, folks? Let's just break this down. We're talking about biological organisms like bacteria or rabbits or foxes or bears. And uninhibited growth means how frequently are they mating and producing offspring? As often as they want. right? They're just having babies and having babies and having babies as often as they can, as often as the opportunity arises, right? So like, female has a baby, and you're like, hey, you want to have another baby? And they're like, okay, let's have another baby. And then they just keep on going. So the phrase uninhibited growth is actually pretty funny, right? Especially because uninhibited, normally you say, how do you eliminate your inhibitions? Well, okay, I'm going a little too far here. The point is, uninhibited growth means have babies as much and as frequently as possible. And that's what we're modeling here. Okay, so the only reason this formula works is because we're assuming that the biological organisms in question are having as many babies as often as possible as they can, which is not what any of us in this room are doing, right? Humans, hopefully, are not practicing uninhibited growth. Unless that's your goal. If you just want to have lots and lots of kids, that's fine. But you're not going to do it forever. You're probably just going to do it for like 5, 10 years, have as many kids as you want, and then you want to stop, right? That's not so in uninhibited growth. Uninhibited growth means you're 50 years old, you're 60 years old. Well, I realize there's menopause. I'm going into a lot of details here. The point is, uninhibited growth assumes as much procreation as possible. Just so we're all clear. All right, so that's the formula. You take an initial population of organisms, let's say rabbits, and then it's e to the kt, where n of 0, right, n naught, like x naught, y naught, n naught, is the initial number of organisms, and k is the constant of proportionality, which is the growth rate. You might want to say k is the growth rate. Now you might ask, why is it that in bank problems with money we use r, whereas in populations that, or questions that have to do with populations, we use k? And I'd say it's cultural and historical that they're using k instead of r. I just want you to know that they mean the same thing. It's growth rate. It's the growth rate of the population of rabbits. It's the growth rate of a bank account. We're all talking about rates. So k still represents a rate of growth, even though it's the letter k instead of the letter r. Okay, so there we have it. That's the formula we're going to use. Now let's read our first problem. This is very humorous. Under optimal conditions. What does optimal conditions mean for uninhibited growth? It means that everybody can be mating with everybody as often as they like, right? So that's optimal conditions. A growth of a certain strain of E. coli. You all know what that is, bacteria? Okay, so what are we really talking about? The bacteria have plenty of food and plenty of opportunity. Food and opportunity. So there's no reason, you've got this little petri dish full of bacteria, you're giving them food, they just keep on growing and growing and growing and reproducing. Of course, bacteria is not nearly as exciting because they just split in half, right? It's just binary fission. A single bacteria splits into 2 bacteria. So not nearly as exciting as it would be for rabbits. Okay, so the growth of a certain strain of E. coli is modeled by the law of uninhibited growth, which is this formula, where n naught is the initial number of bacteria and t is the elapsed time measured in minutes. So just think, minutes. That's how quickly bacteria grow. Within minutes, the bacteria have already split into many more bacteria. So that's why it's so gross when people leave food out on the counter and it needs to be refrigerated. Like if you just have a food and you take it out of the fridge and then sitting on the counter for an hour or two, how many bacteria could have already grown on it? A lot. This is why when your power goes out in your fridge, that's a real bummer. Because if your power goes out for even 5 hours, that fridge the temperature might have raised and a lot of bacteria could have already grown and could ruin all your food. Right? So, from numerous experiments, it has been determined that the doubling time of an organism is 20 minutes. So what does that mean? The doubling time of a bacteria is 20 minutes. So how long does it take a single bacteria to split into? 20 minutes. So you take a single E. coli bacteria, and then after 20 minutes, you've got 2 E. coli bacteria. Right? So that's the doubling time for that little bacteria to split in half. So suppose 1,000 bacteria are present initially. So we can go ahead and do this problem in our head. If you start with 1,000 bacteria at 9 a.m., then how much bacteria do you have at 9:20 a.m.?
2,000.
2,000. And on and on. So then you have 4,000 bacteria at 9:40, and you have 8,000 bacteria at 10 o'clock, and so on and so forth. You could do this in your head. So it says find the growth rate, find the growth constant K. It also says find a function which gives the number of bacteria after 10 minutes or T minutes, and then how long until there are 9,000 bacteria. Now, first of all, we can already answer that last question roughly, right? How long until there are 9,000 bacteria? Would that be right there?
Mm-hmm.
So roughly speaking, how long did I have to wait? 20 minutes, 20 minutes, 20 minutes, a bit. So how long did I have to wait to get to 9,000 bacteria? An hour and a bit, like an hour and 5 minutes. So we kind of already know the answer to part C, right? It's about 1 hour, 5 minutes. How did I get 5? I'm just guesstimating. All right, and of course we're gonna get a real answer to that. That's just a guess. All right, folks, let's do it. How do we start part A?
Well, we know that
How do you always start any problem? Write down the equation. So n of t, the number of people in the population after t minutes, is n naught e to the kt. They want us to find the growth constant k. Well, what do we know? Do we know n naught? Yeah, it's 1,000. What do we? Yeah, what else do we know?
we know
What is t?
20.
Ah, 20 minutes. If t is 20, then that's going to be k times 20. After 20 minutes, how many bacteria should we have? 2,000. Sit with that and make sure that that makes sense, what we just did. All we really knew for sure was that the 1,000 is what you started with. And then they also told us doubling time is 20 minutes. So that means if you plug in 20 minutes, then you should have double the population. So that took a little bit of thinking to realize what else to plug into the equation. They told us the doubling time was 20 minutes, so you plug in 20 for t, and therefore you get twice as much. So now what do? We want to solve for k. Where is k? In the exponent. Therefore you're going to need logarithms. Okay, so let's divide off the 1,000. And once again, that gives us 2 equals 20k. Why did it equal 2? Because it was doubling. So that 2 is not an accident. Okay, so now I'm going to write equals 2 because I prefer to have my exponential on the left. And so this is an exponential form. We convert it to logarithm form, which we already knew we had to do because the unknown was in the exponent. And to solve an unknown in the exponent, you need a logarithm. So now this is log base e of 2 equals 20k. Of course, log base e is really just natural logarithm. So that's natural log 2 equals 20k. And k is being multiplied by 20, so you divide by 20. And that gives us k. The constant of proportionality is natural log 2 divided by 20. So natural log 2 divided by 20, which is 0.03467. Keep as many decimals as possible. Every once in a while I hear a rustling of activity in the audience. I'm like, hey, they're getting ready to leave. What's going on? Oh, it's 10:21. Class is over. All right, so we're done with part A. And we'll keep going from there when we come back on Wednesday. Keep in mind, Wednesday, we're just going to finish these word problems and then look at the practice test. Also keep in mind, I remember the list of people from last practice test who never got to come up to the board to do a problem. So be sure you will get to come up and solve at least one problem for the class. Thank you, folks. If you have any questions, let me know. It's not really a rate in minutes. It's not like it's saying that you get 0.03 of bacteria. It's not saying. It's not saying anything. It's just a constant proportionality. We would have to do that. You want to look more at it. I don't know. I removed those problems from the assignment. Okay. So you don't even have to. Thanks for bringing that to my attention.
And I'm like, if I could just I call software.
And time and struggle. And
So
just
my
knowing
client,
that,
the guy called me, he was leaving me.
knowing that you have one gun is like, what a blessing.
I don't know.
So what you're saying is you definitely want to do it.
I have to.
You just want Ashley to go for this too. Okay.
You're looking better come to class today. No, I said I'm coming. Why are you out here?
Oh, for me.
That was me.